Hi, this is Loma. It's very lucky for me and my collaborators that our paper toward fast, flexible, and robust low-light image enhancement is selected as the oral presentation. I'll make a presentation about this work. First, I would like to show the superiority of our method from three aspects, including computational efficiency, numerical scores, and visual quality. An excellent low-light image enhancement algorithm should satisfy two aspects, including high quality and high efficiency. To this end, we would like to construct an efficient learning strategy to endure the powerful characterization under the limited source. Our contributions can be concluded as these threefold. It is the first work to accelerate the low-light image enhancement algorithm by exploiting learning process. The attribute analysis shows that SCI possesses the operation-insensitive adaptability and model-irrelevant generality, which have not been found in existing works. From the experimental results, SCI redefines the peak points in visual quality, efficiency, and performance on downstream tasks. Next, we introduce SCI in detail. We know that the Retina theory is a commonly used modeling manner for low-light image enhancement. Inspired by Retina theory and stage-wise optimization, we firstly construct an illumination learning with weight sharing and define this process as F. Considering the burden of executing multiple stages that can be in the same status, we would like to construct a self-calibrated module to make the results of each stage convergent to the same state that we call it G. Then, we acquire the basic unit for learning, FGX. The overall framework of SCI is shown in this slide. We need to emphasize that our testing phase just performs the one illumination estimation module, and the self-calibrated module does not appear in the testing phase. We also compare TSNE distributions about whether to use the self-calibrated module in B. It can be easily seen that the self-calibrated module indeed guarantees the convergence between each stage. That is to say, our goal is successfully achieved. A valuable point of our method is that SCI is insensitive to the specific operation, which demonstrates the flexibility of our proposed method. We also find that our method can be easily transferred to other algorithms which are designed based on illumination learning. We consider the work published in CVPR 2021 RUAS to verify this conclusion. As shown in the bottom part, the RUAS with three stages appears the overexposure, but after using our proposed method to train a smaller module, the performance has a big improvement. And this slide shows quantitative comparisons on different benchmarks. Obviously, our method realizes the competitive quantitative scores, especially on some non-reference matrix. Here we show the visualization results of different methods, and it can be seen that our proposed method has obvious advantages in detail preservation, such as sharp edges, appropriate exposure, nature color. In real-world scenarios, our results are better with distinct details, vivid color, and excellent exposure control. At the same time, SCI is more friendly to downstream tasks. In the dark phase detection task, we get highest accuracy and detect more small objects. In the nighttime semantic segmentation task, SCI also obtains the competitive numerical scores, distinct outline, and complete structure. In this slide, we show the results of different decomposed components method and the result of ablation study. In general, SCI has achieved superior performance in both image quality and inference speed. Maybe it would be a brace to enter a new high-speed and high-quality era for this task, and SCI opens a new perspective to improve the practicability toward real-world scenarios for other low-light vision problems.